Okay, so welcome back to the post-lunch session. In this session, Professor Tirthankar Chowdhury will continue with, I think, hands-on discussions on reanimation. So I'm pretty sure that is going to be a very exciting session. So do take part in the interactive sessions and try to have maximum benefit of that. Over to you, Tirth.
Yeah, thank you, Supratik. So let's see how it goes. So let's start the hands-on session. So today's hands-on session, again, if you have taken a look already on the Python notebook, you will realize that today we are going to talk about mainly how to generate the dark matter field, the large-scale dark matter field, based on which we will generate ionization maps, but that will be the next hands-on session. So today it will be the dark matter field, basically. So let me try to share. I hope you can see this. So all of you would have gotten this Python notebook, the Jupyter notebook. And I had also sent you the instructions for how to open it in Google Collaboratory. So we will use Google Collaboratory for this. So if you go to Google Colab, what you can do is you can click this file tab, and then there is upload notebook. And if you do upload notebook, it will give you options so as to upload it from your computer where you save the Jupyter notebook. Okay, so I will just pause here for a few seconds just to see where if there is anyone who hasn't been able to reach this point. So I expect all of you to have a window open with this Python notebook. Okay. Okay, so I'm assuming that all of you have reached this point. Okay, so this is a Jupyter notebook, no problem here. And just to give you some motivation and introduction to what we are planning to do. So as I'm saying here, we will try to generate the large-scale distribution of matter, different redshifts, and study their properties. This will, and then we will try to connect some of these things with what we learned in the perturbation theory class. Okay. Now, if you want to generate cosmic matter, simulate cosmic matter, you should use n-body simulation, strictly speaking. However, running an n-body simulation, although they have become quite efficient now, would still need some computing resources and time in particular. It may take an hour or a couple of hours to just complete one run, which is useful. But then that's not very ideally suited for tutorial. So either I could have run an n-body simulation and given you the data, but then I thought I will do it in a different way. Instead of running an n-body simulation, we will use a 2LPT code. If you remember my perturbation theory class, I said that there are analytical approximations to the n-body, which is either Zeldovich approximation, which is 1LPT. Otherwise, you can go to 2LPT, which is the second order Lagrangian perturbation theory approximation. Now, in fact, there are codes which will do 3LPT and 5LPT and so on, but we won't do that. And for this, we will use a publicly available code. Its name is Music. And it is developed by Oliver Hahn and his collaborators, and it's maintained there. We will use Google Collaboratory. I understand that you people have been using SciServer, but in this case, we will use something different. This will allow you to run the Jupyter notebook, but it will also allow you to run the shell commands, like what you will run in a terminal. Okay. But we will be using a free version of Google Collaboratory, not the pro version. So what happens here is the moment you start the runs, it will block a virtual machine for you. But this machine will be there for you only for a fixed amount of time. So for example, if you don't, you are inactive for an hour or so, it will just decouple you from the machine and give that machine to someone else, because the whole world is trying to use them. Okay, so they want to optimize it. And in any case, after a few hours, even if you are running something, I think they will stop it. Okay, and they won't allow you to run. But so we will keep it short. But that few hours is maybe 6 hours, 8 hours. I forgot what that is. You can check. However, this notebook will be saved in your Google Drive. So you won't lose anything you are writing here. Of course, the moment you get disconnected from this, what happens is everything goes. I mean, even the data you generated will also go. So you have to generate the whole thing again. One option is you can, it's possible to save your work on your Google Drive through this. But since I don't know how much space you have in your Google Drive and things like that, so I thought we will keep it simple and just do the default version. Okay. So we will be using these transient virtual machines. And remember, if you like, I'm sure throughout the class, there won't be any problems, hopefully. But as I said, if you keep it inactive for some time, I mean, everything will go. You have to start from the beginning. Okay. But since everything takes so much less time, it's fine. Okay. If any point you have questions, just ask me, like in the lectures. Okay, so let's get started. The machine they allocate is basically a Ubuntu machine. So people who are comfortable with Linux and Ubuntu will find this very straightforward, but for others also it should be fine. So the first step is you have been given this like machine which has nothing basically. So we have to start installing things. And remember, when you get disconnected, you have to come back and start from this point again, because you have to install everything. You will be allocated a machine which is like almost pristine. So we shall install some of the packages which are needed. We shall install music. We will install another package named script. This is a package written by me and my collaborators. This is for generating ionization maps. Now today we won't generate ionization maps, but we will still use script, because in script we have given some utilities which helps in analyzing the simulation data, this music data. So we don't have to write all the codes from scratch. Okay, we will just use the routines we have in script. So let's get started. So we are now in the first cell. All of you can see this, hopefully. So I will just run you through the commands very quickly to understand what we are doing. So, okay, let me just do one thing. I will just clear it. Since I was running, just give me a second. So I will clear all output. So it will be hopefully like a cell which you are seeing. So first we do a cd/content. This is the directory that is like present in this machine allotted to you. So we go to that directory just to be sure that all of you are in the same directory. We all install two packages. One is FFTW3. Another is GSL. FFTW3 is for Fourier transform. GSL is like a GNU scientific library for various mathematical functions. Okay. FFTW3 is needed by music as well as by script. GSL is needed by music. And it is very easy to install. Okay. So in Ubuntu, there are commands called apt-get. That is how you install packages. So you do it this way. This greater than /db//null, what it does is while installing the package, it will write various outputs, okay, status outputs. So we don't want to see all of them. So we will just redirect them to a black hole. Basically, we won't see them. And the error messages will still come up. So we will install these two. We will install music. Installing music is basically, I mean, first is we need to get music from the Git repository using a Git command. Okay, so fine, this is what it is. Then we will go to the music directory. We will make a change in the make file so as to have the compilation easy. And then we will do a make. This is compiling music. So this is all what one is doing. Installing these two packages and installing music. So you come here and do a shift enter. So if you do a shift enter, it is running. You see it is running here. This circle with something is showing that it is running. And we will wait for some time because it's taking some time to run. Okay. So it has gone to the content and then it will install various things. The outputs can be different for different people, but basically it will run. So we'll wait till this thing does. If anybody can see here, you will see it gives you the status. It's saying executing some command. Okay. And this is the time which has been spent. Okay. We are at 30 seconds now almost. Don't worry about these error messages. Things should be fine. So have all of you come here and I mean, is there anyone who hasn't come here and is not able to run this? Okay. There is a chat message I see. Yeah, don't worry about the error messages. Obik Bhattacharya has asked. Just don't bother at this moment. These are, yeah, the compiler tries to be a bit smart than usual, and then it tries to give you warnings. These are fine. Don't worry. Even I'm getting those messages, if you can see. So in the whole thing, what you will find is installing music takes the most of the time. Okay. Somebody has asked whether I will be explaining the make file. I am not going to do that now. If there is time towards the end, I can. That's just too much details in this. If you're asking about this command, just this command, I can just tell you what I'm doing. What happens is music by default uses a format called HDF5. But we are not going to use that format. Okay. So what I have to do is go to the make file and change something from yes to no. So there is a variable called have HDF5. By default, it says yes. But we want to say we don't have HDF5 as if, because we will not use HDF5. So I have changed that yes to no. So that is all this command is doing in the make file. You could have also opened the make file and manually edited it. That is also possible. Okay. For example, you can do the whole thing in your own machine without going into Google Lab or anything. You can just open the make file and make the change. That's also equivalent. Okay. Perfect. So for me, it is over, and you see it says it took roughly 2 minutes for the whole thing. Here it says 2 minutes, 1 second. Good. And this is the longest time it takes. So now we will do the same thing, but now we will install script. Script also, you have to do a git, and then instead of make file, script comes with a Python wrapper. So what we have to do is we have to do a Python install here. Okay. So again, nothing to explain here, but we'll just go to the content thing so that there is no confusion. And then we will just go to this cell, do this. It will still give some error messages, but otherwise it will install. So this is script which is needed for ionization maps. In the next tutorial also, we have to do all these things once more. Because by the time we go for the next tutorial, I think on Tuesday, this machine will be gone. Okay, you won't have, you will be given a new pristine machine by Collar. And this one you see is completed in 24 seconds. Okay. Now, basically the installation is over. You have music installed and you have script installed. Maybe later, let us go through this. I will show you where it is installed and where the files are. Okay, but let's just carry on for the time being. Now, everything is installed. Now, actually, what we are doing is we are actually writing a Python code. Okay, inside this notebook. That is the main thing we are doing. So in Python codes, what the first thing you do is import various packages. Okay, Python gives you various packages. So we have installed NumPy, which is like a mathematical numerical analysis library, extremely useful. We have installed, we will import PyLab, which is for plotting. It's an alias for what is called matplotlib in Python. We will import script. Script is what? Script is this code we just installed. Okay, for making ionization maps. We won't make ionization maps, but today, but we'll still import. And from script, we will import 2LPT. These are some utility routines in script which help you in running, help you to run the music code. Okay. So we import, we have imported, okay. So there are no error messages, everything is properly imported, it has found everything, okay. So now we will run music. So to run music, we have to set some variables and then run it. So basically, again, essentially we are writing a Python code. So first, we have to tell where is this music installed. Okay, so the music, the way I have written everything, I know it is installed here. Okay, remember we went to the /content directory, then we cloned music, then we did make file and things like that. So I know that music is installed here, so I have to give the full path. Done. Now comes the simulation itself. Okay, what kind of simulation we want to run? So here I have chosen a box size of 128 H inverse megaparsec. CMPC means co-moving megaparsec. As I said in the perturbation theory class, in perturbations you will be most of the time using co-moving units. So just to make sure we are using co-moving units, I just say C here. So I have chosen a box of 128 H inverse megaparsec. Nothing special, I have just chosen. Then, at what redshifts do you need the outputs? Okay, so we don't want to overdo. We will just take outputs at 3 redshifts just to make sure things run quickly and we don't lose all the space in the machine, in the Google Colab machine. Okay, nothing. See, you are, I mean, your disk space or nothing is being utilized. Okay, so it's happening somewhere. I don't know where this machine is. Nobody knows where this machine is. So what I have done here, that I have chosen 3 redshifts. One is a reasonably high redshift, 50, where no structures are, as you have probably formed, like dark ages. These are the dark ages time. No galaxies, nothing. 10 is somewhere the first galaxies may have started forming. And 3 is a reasonably low redshift, okay, for our purposes. So I've chosen these 3 redshifts, and in principle, you should be able to play with different redshifts you choose, okay. Now these redshifts are passed as a NumPy array. NP is NumPy, which we have imported, and this is an array which is passed. So both in C or Fortran, you would have played with arrays, right? So this is that array. Okay. You could have passed this Z as various other ways also. I mean, there are utilities in NumPy like linspace and things like that. So today I won't go into this, but you figure out a way to choose your redshifts. Okay. Next, you have to tell in which directory do you want to store the outputs. Okay, because you want to access the outputs later, right? So you should know where it is stored. So I have told that you store the output in this directory. Okay, there is nothing special about the name of the directory. I have chosen my way of naming. So I say N128 means number of particles will be 128. L128, that means the size of the box will be 128 in H inverse megaparsec. And music to LPT is obvious. R1 means this is my first realization. I'm running one realization here. Okay. If I run one more, I can call it R2 or whatever. So you've come up with your own naming convention, but for the moment, we'll use this. You can then have to specify what will be the name of the files you want to store the data in. So I have said that the name of the file should start with snap. You can use whatever root you want. DX is the grid resolution. So I have kept it 1. 1 is a good number to have. Don't change it unless you really need to. 1 means my box size is 128 H inverse megaparsec. My resolution will be 1 H inverse megaparsec. That means I will have 128 cube particles because my box volume is 128 cube and mean interparticle distance is 1 H inverse megaparsec. So I will have 128 cube particles in the box. This is a moderately sized box or a small box basically. As I said, the cutting edge simulations will use 1024 cube or 2048 cube particles. And for that, you need to go to high machines. Something like Google Colab or your laptop won't be able to handle those. In Google Colab, you can easily go up to 256 cube. Okay, so you change the box size to 256, it will run easily. It will take a bit more time. Next is cosmological parameters. You know all these things. Omega m, omega lambda, I have chosen it to be 1 minus omega m just to keep the universe flat. Omega b, omega baryon. The Hubble parameter H. Sigma 8. Sigma 8 is the normalization of the primordial power spectrum. NS is the slope of the power spectrum. Okay, so these are the cosmological parameters which needs to be passed. Okay, to the simulation. If you want a different cosmology, you can change these things easily. And final thing is a random seed. As I said, what you are going to generate is a random realization. Okay, so you have to give a random seed. If you give this seed every time, it will generate the same realizations. Okay, the pattern will be the same. If you want to change the pattern, you have to just change the value of this seed to whatever number you want. So let us run this cell then. And there is nothing really to run. This is setting the variables. Okay, so it has run in 0 seconds because there's nothing. Then we have this is setting up the variables. Now we will actually run music. To run music, remember I want everything to be stored in this directory. So I have to create this directory, and just to be on the safe side, I just remove the same directory in case I have created it earlier and it stays. I don't want this confusion that maybe earlier I have made some runs and then some files stay and some new files get created and then there is confusion. So just to be on the safe side, I will do a RM. RM means remove this directory, and then I will make the same directory again. Okay. Again, as I said, the first line is just for safety. In case the directory has been created earlier because I ran this code earlier sometime and this directory remains, I just wanted to make sure everything is clean. And then this command comes from script. Okay, so 2lpt.run music, and these variables are given. Okay, so it will run music, and let me just do a shift enter, and this is running. Okay, so it says number of particles 128 cube as we expected, and then it is running music for z equal to 50. The output is in this directory, and the name of the file is snap_000. Snap, remember, is something you mentioned here. Outroot is snap. Okay, if you use some other outroot, it will name the files up accordingly. Then I also asked it to put a thing at redshift 10. So that is the next snapshot. It is named 001. And then another snapshot at 3, it's named 002. 3 snapshots, it ran in 9 seconds. Okay, roughly 3 seconds per snapshot.
Sir, can I run this?
So I don't know where you are running this. Where is this IPython and other things coming? You are running in your own laptop, is it?
Yes, sir, in Google.
Are you running in Google Colab? No.
Yes, sir.
Then you haven't run some of the previous things. Okay. Go back and start from the beginning. Keep running everything properly. Okay. I have never seen this command, this error message. I'm hoping that for everyone else, things are fine. So now it has run and these files are there. Okay. I can again show you, but maybe later where these files are. So if at some point we had run a gadget, then
Hello?
yeah.
Can you hear me? Yeah. So are you accessing this music, music's package from the script package here via this tool LPT function?
Yeah. So music has been installed, and then a script has a routine which will run music.
Okay, yeah, understood.
Okay, but this is kind of convenience only. In principle, you can install music and run it yourself without any reference to script. But then you have to do it on your own. You have to install it, which is installing is fine. I have shown it how to do it. But then what you have to do is there is a configuration file in music directory which you have to modify and set all these things there appropriately. And then run music from command line, just like you run. You have to say, you can use MPI run, for example, if you are running parallel process, if you want to run it parallelly. So the music executable and then the parameter file name, and it will run music. But again, just for convenience, I'm using script. As I said, this is convenience, this is not essential. Okay. Let me pause here for a second in case anybody has any trouble or anything.
Sir, it is saying that Fatal cannot change to music, no such file or directory.
And then it is stopping?
No, it is not stopping.
That is fine. So this came in, as I said, you just ignore. If you see my screen, I also got that, but that is not a problem. As long as it completes, if you wait for 2 minutes, this thing will complete. But make sure you do everything properly and don't change anything in these. Okay. So now that music
Sir,
is
what
run, sorry?
Sigma 8, sir.
Okay. You haven't learned Sigma 8. Okay. So Sigma 8 is basically you take the density field, you average over regions of H inverse megaparsec, okay, and then calculate the amount of fluctuations you have. In effect, this is nothing but the power spectrum times a window function and integral over k. Okay. So I will, let me see towards the end. If I have, if I have time, I will just show the formula, how to get that. Okay. For the moment, have you done AS, the normalization parameter for dark matter power spectrum? In any of the cosmological parameters, I don't know, in the previous lectures, CMB lectures, for example. NS and AS, the amplitude of the scalar power spectrum.
Yes, I think that has been discussed, but let the speakers, let the participants.
Yeah, participants say, yeah.
Okay,
So
yes.
for the moment, think of this. Somebody said yes. So think of sigma 8 as a proxy for AS. Okay, just take it as that. Okay, it is AS in a different unit, in a different way. And I will connect AS to sigma 8 towards the end of the class if I have time. Okay. I would also say AS is something which is normally used in the CMB community. Sigma 8 is something which is used in the large scale structure formation community. Okay, so but these two are related. Okay, now let us come to, we will now analyze the simulation output. Simulations have been run. If you had run actually gadget simulation, I mean, if you have run an in-body simulation, you would have reached this point. For example, it would generate some output snapshots. And if you generate the output snapshots, after that, you are analyzing the simulation output. It's as if, so what we have done is we haven't run an in-body simulation, we have run a proxy in-body simulation. Okay. So again, for analyzing, we will write another Python code. Here again, we start by importing some OS and sys are some Python packages which help you in running system commands. Okay. Config parser is something which helps in reading the music configuration files. Okay, config, it parses the config files. Okay, so let us start. So here, first I have to, now I'm analyzing. So for analyzing, first I have to tell the code where is the data stored. Data is stored where? Data is stored where I generated it. So it is the same directory as where the data was put. Okay, so same. So in fact, you could have put data path equal to what did I call it? Out paths. That would also have worked. Data root is snap. Okay, so that's also something we set. Okay, there is nothing, I mean, if you had set it to something else, you would have just mentioned it here. If this code generates some files, where will we want to store it? We will store it in data path / script files, a subdirectory under data files. Okay, again, it's up to you. If you want to store it somewhere else, store there. But keep a system. Okay, so I prefer that everything is stored under this directory. So fine. Okay, these are details how the loop is done. So let me not go into it. If you just go through the code, you will understand what's going on. And if later maybe I can understand. This is an array where I will store the music data. So now it is empty, and I will keep on appending data to it. And since I will be making the plots also, let me just initialize the plot. So this is the figure I am initiating. So this has a size 12 by 5 in inches. I will make some subplots. So this will have 1 row and 3 columns. I will plot slices. If you remember in my lecture, I was showing these movies with slices. So where will the slice be centered? The center is at 0.6 in units of the box size. So if the box size is 1, I want the slice to be at 0.6. Okay, there's nothing about 0.6. You can change it to anything. And the thickness of the slice, I have put it to 2. Okay. This 2 is in H inverse megaparsec. Okay, that's the only trick. Now I want to read all the snapshots. So I will run a do loop, okay, or a while loop. So first I convert, So snap is, remember the file names are snap underscore 000, snap underscore 001, snap underscore 002. So my loop will run from 0 to 1 to 2. And for each of these values, I will convert the number 0 to a string, which is 000. If it is number 1, then I will convert it into a string, which is 001. So this is the way to do that. And then this gives you the snap, basically the full path to the snap. Data path is where it is chosen, where it is stored. Data root is that snap underscore. Snap string will be like 000. Okay, so this will actually make the file name consistent without you trying to supply it manually. If loop is 0, it has to read only the cosmological parameters only once. So it just reads the cosmological parameters from a configuration file. Okay. You don't have to read it every time. You can do that, but since cosmological parameters are not going to change in between snapshots, so it's sufficient to read only once. Now, just to be careful, I just run these parts and make sure that the music snap exists. Otherwise, it will just give an error message and stop. Now, if the music snap exists, it will read the music data. Now in Python, there is something called class. Okay, so this is a very powerful structure of Python. So this is a script routine which will read this Python data, and it will store various aspects of the data in this whatever data structure. Okay. So it will store the cosmological parameters, the box size, the redshift, the particle positions, the particle velocities, everything. Okay, whatever is required, it will just store here. Okay. So it just stores in this. And then once it stores, we can access various aspects of that data. And just for future purpose, we will also calculate the density and velocity fields. We'll just keep it once and for all. Okay. So the music data is read and stored here. Okay. This is a variable. You can change this name to whatever you want. This is the function, okay, which defines this variable. So again, this is where the script utilities are helpful. Otherwise, you have to run your own code to read the particle positions, particle velocities, cosmological parameters from and stored them. Now we will have to define that slice which we are plotting. So slice is what? It is the center, but center was in the box, like in units of box. So I multiply by the box. Now you see box is what? Music data dot box. So music data has various attributes which you can access by putting a dot. So music data dot box will give you the box size of the simulation. So I say you go to this center and my thickness is dx. So you go half dx on both sides. That will be my slice z-min to z-max. Then I do a mask. Masking means I choose only those positions. You see music data dot pos is the positions. So it is an array which has 3 coordinates for 128 cube particles. But I don't want to plot all the particles. I want to plot only those particles whose third coordinate, that is the z coordinate, is between z-min and z-max. So that masking is done here. So music data pos 2 means since the indexes run from 0, 1, 2, 0 is x direction, 1 is y direction, 2 is z direction. So z direction has to be, the position in z direction has to be less than z-max. Also, at the same time, it has to be greater than z-min. It's a logical AND operation. Then I just do a scatter plot. Then I beautify the plot. I want to make the plot aspect ratio 1. I set the x limits and y limits from 0 to the box size. I put a nice title, which will give you the redshift. I set the label of the axis. And then what I do is whatever I have read this music data, I store in this array, because later if I want to use, I don't have to read everything again and again. I can use this array. And then I keep on running this loop, and it breaks when it doesn't find the next snapshot. Okay, if it doesn't find the next snapshot, it will break. And then I do a layout, a beautiful layout, and I asked it to show. So I will do a shift enter. Okay, so it will read. It will take some time to generate everything, and then it will show. So now the question is, so this is our first output which we are seeing. I hope everybody has gotten here. So I will wait again for a couple of seconds. So what you see are particle positions. There are dots here, right? Each dot is a particle or a fluid element or whatever you think of. These are at different redshifts. It's the same slice plotted at different redshifts. 50, 10, 3, and you see this is the box. 128 H inverse megaparsec is the box. Now you see at 50, it's very uniform. Okay, you see almost, but there is a small structure, very small structure, but it's basically uniform. This would correspond to a largely homogeneous universe with very minor inhomogeneities. Redshift 10, you see things have moved a bit. Okay, some places have become places which were overdense have become more overdense. And some places are white, means particles have moved away from that place. Okay, these are voids. So this is, you see gravitational instability in play here. And at redshift 3, you see the cosmic web forming. You see these filaments and these voids and so on. So this is basically a simulation of structure formation which you have run in a simple way. Okay, and then you are visualizing them. And these are the kind of plots you would see. In fact, I mean, for example, when I was doing a PhD, papers will be written if somebody produces something like this, because computing power was so scarce then. Okay, but now of course you can run on your laptop very easily. So you see these voids and so on. Just remember a few caveats. We have run a 2LPT, not a full n-body simulation. So there will be inaccuracies at small scales, but it captures the broad picture quite nicely. Okay. Okay, so let me, before moving ahead, take some of these chat messages. So Obik Bhattacharya has asked me to explain this statement, this mask statement. So as I said, there is this music data dot position which stores all the position of the particles. So this is 128 particles are there, but we don't want to plot all of them in a 2D slice, because then it will be like everything will be on top of each other. So we'll plot only a slice. So I have to choose only those particles which have z coordinates between z min and z max. Okay, so that is how you define a mask in Python. You can basically choose a subset of values in the array based on some condition. Okay, the condition here is that the position, the z coordinate of the position should be less than z max, and the z coordinate of the position should be greater than z min. Both conditions should be satisfied. Okay, so that is given by this logical and within this and I have given two conditions, two logical conditions. If they are satisfied, they are stored in this mask, and I mean their mask is true, otherwise they are false. And when I plot using scatter, I don't plot all the particles, I plot particles for which this mask condition is satisfied. That's all. Okay, so that is how the mask works. And the second question is, somebody asks whether the shades are vacuum. vacuum at our resolution. Okay, so suppose I had gone to higher resolution, you may see that there are particles there as well. So they are not vacuum, they are low density regions. Okay, so that's how you look at it basically. Okay. Just give me a second. Okay, there's nothing more. So let me go to the next part. There is something I cannot remove. Just give me a second. I will stop sharing and then again share. Huh? Just give me a second. Yeah, I'm back. Hopefully back again. You can hopefully see the screen, the tab again. Okay. So this is particle positions. Okay. I mean, and now I hope, given this code, now you can run for any redshift and plot particle positions in any way you want. I mean, you can go to a different slice or whatever. Okay, you will see this structure changing, but the qualitative thing will still remain. Now, let's do a bit more, and now I won't go into so much details. Now, what I will do is I will plot the positions as well as density, because I have already calculated the density here. I have already calculated the density fields. I have also calculated the velocity fields, but in this course, we won't be doing anything with the velocity fields, the peculiar velocity fields. So let us do the density field here. Okay. So again, I will plot the figure. I will go to the same position, 6, same thickness. I will loop over the music data, because I have stored it into this music data array. Z means Z max, mask, everything is defined, and I will just plot this thing. Okay, so I'm not going into the details. This is just plotting. But this time I will plot. If you see, I have chosen my subplot to be 2 by 3. So there will be 2 rows and 3 columns, and this is what you will get. So the upper panel is same as the previous thing, the particle positions. The lower panel is the density field. So the particle positions, which are positions of particles, have been converted into a continuous field, okay, by a smoothing algorithm. Now you see the fun. At 50, you see the density field is just uniform. You have to really work hard to see any fluctuations. There are, by the way, but and at 10, it is showing something. And at 3, it is quite prominent. And you can see wherever there were more particles are positions which are like yellow, high density regions. And where there were less particles would be like voids, okay, low density regions. So this is the density field, the cosmological density field, which corresponds to the particle position. I mean, in principle, they are like, they contain very similar information, but one is like discrete particles, the other one is a continuous field. Okay, so this is like rho as a function of x, y, z. That is individual particle, their position scale. So that is the difference. Okay. Again, let me pause for a few seconds. Hopefully people have reached here. Is smoothing algorithm a class method from music? It's not a class method from music. It's a method which is defined in script. Okay. And what we have used is a smoothing algorithm called CIC, cloud in cells. So I haven't discuss these things, but there are ways to smooth the particle fields. Basically, what you have to do is you have to first choose a grid in the box. That grid can be anything. And in each grid, you find out the particles within each grid cell. And then you have a very sophisticated way of distributing those particles in various grid cells. You can think the easiest way of generating the density field. You divide the box into grid cells. So grid cubes, basically, small cubes. And within each cube, you find which particles contribute to that cube. Since you know the particle masses, you can calculate the density there. And so at each box, you will have the density field. So that is the easiest way of generating density field. It's called the nearest neighbor scheme. Sorry, what am I saying? It's the, I will come back. What's the name? I just forgot. What is it called? Okay. I will get back to this. Okay. But then CIC is cloud in cell, which is a slightly more sophisticated way of generating the. The first one is not nearest neighbor, it's the nearest grid point, NGP, nearest grid point method. So you just put the particles to the nearest grid you have. But cloud in cell is a more sophisticated one where you distribute the particles in nearby grids based on the weights, based on the distance from the grid points. Okay. So anyway, those are details. You can have more sophisticated methods like triangular cells and so on, but I haven't discussed that. Now we will do something more quantitative. This is good for visualization. Let us find the properties of the density field. For example, let us try to find out the minimum and maximum of the density field, like the density contrast array, density contrast. Then let us find the median, the standard deviation, the mean of the density contrast. And then also let us find out the PDF, that means the probability distribution function of the density contrast. So what I'm doing here is I'm looping over all the music data I have. In the first statement, I print the redshift, the mean of the density contrast array. Density contrast is the density contrast which I have calculated from the particle positions. Then I calculate the standard deviation, STD, calculate the median, print it. Then I print something more. I again print the redshift. I print out the minimum value of the density contrast, the maximum value of the density contrast. Okay. Then I do a histogram. Okay, that is the PDF of the density contrast array. But while doing the PDF, what I do is I take the density contrast array and multiply by 1 plus z. This is because suppose the density contrasts were evolving in the linear theory. In the linear theory, we know that density contrasts evolve as D, the capital D parameter. And that capital D is in a matter-dominated universe, D is just A. Okay, so it evolves like A. Now, the redshifts we are considering are basically lambda doesn't play any role there. Okay, these are reasonably high redshifts. Lambda, it is dominated by omega matter basically. So in that case, D is proportional to A. So if I multiply the density contrast by 1 plus z, and if the density contrast evolved as linear, then all density contrasts at different redshifts should be same basically. So what we are saying is we want to see how the density contrast evolves more than the linear theory. I mean, okay. So anyway, without spending much time, let me just run it and then we will see. So it has run very quickly. So first it says redshift 50. The mean is 0 basically. 10 to the minus 11 is numerically 0. Standard deviation is 0.05 roughly. Median is also roughly 0. It's very small. Okay. Remember, at redshift 50 is very early times, and there we expect the random field to be Gaussian almost. And the minimum and the maximum you see is minus 0.22 and plus 0.22. So you see there is a symmetry. So clearly this is Gaussian. Okay? And we will see that. Then at redshift 10, the mean is 0. Remember, by definition, the mean of density contrast is 0. The standard deviation has increased from 0.05 to 0.22, which means the fluctuations have increased. The mean has remained the same. The fluctuations have gone up and down. So this is gravitational instability. The median is very close to 0, but you see it's not really 0. So there is clearly asymmetry which is setting in. So it's going away from the standard Gaussian random. The minimum is minus 0.6. The maximum is roughly 2. So again, you see the asymmetry is setting in. By the time you hit redshift 3, the mean is 0. The standard deviation is quite large, 0.65, 0.66. The mean and median are very different now. So clearly the distribution has become skewed. Minimum is increased to minus 0.83. The maximum is 13. Okay, so clearly it's not linear anymore. This is the PDF of this quantity delta 1 plus into 1 plus z. If everything evolved linearly, all these curves should be on top of each other. Now the redshift equal to 50, you see it looks very Gaussian. This one. At 10 also it is reasonably Gaussian, but it has moved. Okay, the peak you see has shifted from 0. And there is a tail which is picking up. And by the time you had redshift 3, it looks very different. So this is the statistics of the density field. Okay, this is a quantitative thing which we are seeing. And this is what makes it interesting. Okay. So again, you can play with this a bit, but yeah, I mean, and then I do what is called the power spectrum, the thing which I talked about in the perturbation theory class. Again, there is a utility routine in script which will compute the power spectrum. And you have to just give them the density contrast. You pass the density contrast. You pass the box size. You tell how many bins you want in K, whether you want log or not, and whether, okay, let's leave this, whether you want to deconvolve or not. Okay, so this is just a complication. And then this gives you the power spectrum. What I'm plotting here is K cube. So it gives you K and power spectrum. And this is a count. Just forget about it for the time being. What I'm plotting is K versus K cube P of K by 2 pi square. Okay, I have made a mistake here. It should be 2 pi square. Where is okay. So if you can make this change, okay, let me leave it at this moment. It will, I mean, the basic thing is fine. It's just, it should be 2 pi square. Rather than that, it has become 4 pi square. Okay, because I put an extra bracket here. But then this power spectrum also I multiply by 1 plus z whole square. That is to account for the fact that if it is linear, the power spectrum, which is like delta times delta, will evolve as d square, which is a square. So if I multiply the power spectrum by 1 plus z square, and if everything evolved linearly, then they should be on top of each other. Now let's run. So this is the power spectrum for 3 redshifts. Now the first thing which should strike you is, okay, this is K versus this power spectrum. K small means large scales. Remember, K is inverse of length. K large means small scales. This is the part which is small scales. At large scales, these 3 are on top of each other. There are virtually no differences. This is because at large scales, the density tends to remain linear for a longer time. In small scales, the nonlinearities pick up quickly. Okay. So these scales have remained linear. So that is why they are on top of each other, because I have scaled out the linear evolution. Okay. Actual power will be different, but they will be different exactly by what is predicted by the linear theory. That's the only thing. But at small scales, you see, as you go to lower redshifts, it picks up more power. So that is showing you more nonlinearities at small scales. So that is the power, I mean, that is the information which is contained in the power spectrum. Okay. Okay, so these are the basic things I wanted you to show. Now I would like you to play a bit with these codes. Okay, there was a question at z equal to 3. Okay, why is it a step function on the left and what is right side is more Gaussian? It's not Gaussian, it has a long tail, so there is no Gaussianity here. What you need to remember is you go and check the definition of density contrast. So it is rho by rho bar minus 1. So the minimum value of the density contrast can be minus 1. It cannot go below minus 1. The maximum value can be infinity. So it's a weird quantity which can go from minus 1 to infinity. Okay. So at the minus 1 level, it has to fall sharply down so that it doesn't go below minus 1. Of course, I have scaled it by 1 plus z. So in this case, the minimum value will be 4, minus 4, because I multiplied by 1 plus z here. But on the right hand side, there is no limit. It can go up to infinity depending on how much nonlinearities it pick up. So this is how the density field, in fact, this is the density distribution, how it looks like. Okay. So, yeah. Okay. So, yeah, so that is all I wanted to do here. Let me do one thing. If you in Google Colab, if you want to look at, sorry, these are the table of contents. If you want to look at the files, you can click here. If you click here, it will give you the directory structure. Okay. So this is the directories, and some of them, I mean, all of them are actually created here. Okay. So you have this script, you have this music directory, and this is the directory where we stored the data. If I go in this directory, you see there are all these files which are created. In particular, snap 000, snap 001, snap 002 are the snapshot files. And then there are various information files. I mean, if anybody is interested, you can open and see. Okay. If I now want to go to the music directory, this is where music was installed. And you see there is this make file, there is this music executable, there are a lot of .o files. And then if you go to the source directory, you will see the actual C++ files. Okay. So this is the music directory. This is the script directory where various codes are there. Okay. So script is essentially written in Fortran, but it is wrapped in Python, so the user can interact with the code in Python. It makes things easier. So these are basically the files. And similarly, I mean, there are many features of Google Colab which you can try. Okay. Good. So now what I can suggest is you play a bit with, for example, you can try to change the position of the plot. Instead of 0.6, maybe you try some other position, 0.19 or so, and just do a shift enter. So you see it is similar, but it is different. It is a different slice now. If you remember the previous one. And similarly, if you come here, do 0.19 in the next one, you will plot both the density field and the. So this is the density field and the particle positions at the same time. Okay, so you have that control here. Okay. Before I go ahead, let's all make this change. So what I suggest here is you drop this bracket. You drop this bracket. Okay, then it should work. Okay, so this will make it k cube. Yeah, so nothing changes, just the values have changed. Okay. Somebody has asked, can you explain the last graph again? So this is the power spectrum, k cube p of k by 2 pi square, but scaled by 1 plus z square. So you see the power is smaller at large scale. So these are large scales, these are small scales. The power is smaller at large scales. This is 1. Okay, I mean, and these are smaller. So at these scales, the fluctuations are still linear. And since at these scales, the fluctuations are still linear, they evolve under the linear theory. And since I have scaled out the linear theory by multiplying by 1 plus z square, all the curves fall on top of each other. However, at small scales, the power is much larger than 1, the fluctuations of the density contrasts. So clearly, they are not anymore described by the linear theory. So here you see deviations. Okay, so these are not explained by linear theory. In fact, at lower redshifts, you have more power. That means more non-linearities have picked up. No, and that is also shown in that PDF because it is clearly not Gaussian anymore. Okay, so that is what it's coming. So this is basically the power spectrum of the density field. And this in principle is observable. Okay, this is how we know about, this is how we constrain a lot of structure formation. Now, one thing you can do very easily is instead of running a 128 H inverse megaparsec box, you can run a 256 H inverse megaparsec box. That will take a bit of time, but of the order of minutes, not large. So you can change here, but then you have to change the out path also. You may want to store it in a different folder so that these things don't get overridden. Okay, so we can try that. I will make it 256. I will change the content of the folder to 250, the name of the folder to 256. Rest I will keep the same. And I just put a shift enter. And then I will run, but while running also I have to make sure that I stored the files in the same directory. So, and I have to make sure these directories are created properly. And then I make the run. Now you see it is taking, earlier it took what, 9 seconds. Even then this is quick actually. No, it's not quick. It's still running. So it's running for z equal to 50. So you see it's already 13 seconds. It hasn't run even one snapshot. So it has become slower, but you will get a larger box. That's the best part. So you see it took almost 30 seconds to run on one snapshot. Then it's running the second snapshot. Now it's running the third snapshot. It's almost a minute already. So you see. And if anybody is looking here, you see a new directory is already created. Okay. Okay, I don't know what is, we should put a bracket after 2 pi square. I don't know what it is, but whatever I did is working. So you figure out your own way of running. So you see it has taken 1 minute, 1 minute 15 seconds to run. Earlier it took 9 seconds. So you see, now we will analyze the simulation output. So I have to make sure that I go to the correct directory. Otherwise, things will be messed up. Okay. So I don't think I have to change anything else. No, nothing. So I run it. So even this will take a lot of time. Oh my God, you see there are so many particles. This has become like too congested. Okay, it's showing up very badly in fact. So let us do one thing. Let us make these points a bit transparent and let us reduce their size and let us see how it looks. So we have to do a trial and error to get these things right because this is a visualization. Slightly better, you see. It has picked up these things. Okay. Maybe, I don't know, I can try to make it slightly smaller, maybe or we can just go to the density plot directly. Why spends time in making the particle plot? We will go to the density plot directly. Next. So this is slightly better. So it is up to you now. Okay, so you see this voids and things like that. But now the box size is different, 256 cube. So this is that density plot. Okay. So you see similar, but yeah, but this has more information in some way. We can do this also without any difficulty. These numbers would have changed and you see this was Gaussian and things are different here. And finally the power spectrum. Okay. And you see this is the power spectrum. Yeah. So and so on. So as I said, it's actually quite easy. I mean, we could do it in no time, few minutes. This is the advantage of 2LPT, but remember, I should say 2LPT is not fully accurate. Okay, if you really want to do accurate stuff, you have to run a full simulation. So, okay. Now, what I suggest is you try these things a bit more. For example, you can change the random seed and run another realization, store it in R2. Okay, store it in R2 and then make sure you run those things. Okay, and if you are comfortable in Python, you can plot the R1 and R2 side by side, but I'm not going to do that here. Okay. Somebody asked what change did I do in the power spectrum? It's this line. Look at this quantity. I have made some changes here. Okay. So just check that. Yeah. So whoever tried to change it not properly, you will get an error. So look at it carefully and copy this part. Okay, so this is for the person who was asking about, this is Vashwati Mondal. So make sure you have copied this part correctly. What package to use for full n-body simulation? You can use a package called Gadget. Gadget 2, Gadget 4, both are publicly available. And the good thing about Gadget 2 is the format it will give, the output format will be exactly same as what we are using here. So you can use these codes to analyze the data without any problem, if you are able to run Gadget 2. Gadget 2 will run on your laptop. It will take some more time, but it will run. By the way, I mean, you can convert these. If you are, for example, using a Linux machine, you can just use these things on your own machine. You have to make appropriate changes. For example, that / content directory may not be in your machine. So you have to change appropriate paths. Okay, but you will be able to do these things on your Linux machine, particularly if you are in a good. So somebody is saying N25, okay. See, I mean, don't switch off your brain completely. I mean, most likely you haven't made the changes either here or here or here. I don't know where. So it's not like computer has its own mind and will try to do something on its own. It will do exactly what you ask it to do. And make sure when you change, you run every cell one by one. My feeling is some of you are just running the last cell or something like that. Okay. Every cell, these are cells basically. This is one cell. That is another cell. So you have to run every cell one by one. Okay. There are options like you can go to a cell and either you can ask it to run everything from beginning, or you can say go to a cell and ask it to run after, means it will run that cell and everything after that. So there are many sophisticated ways of running, but you have to understand the logic and run it appropriately. Okay. But what I want you to understand is that you should be able to now go through this code and code it yourself for different kinds of simulations. For example, instead of these redshifts, you can go to other redshifts as well. Okay. And try to do the analysis and see how things evolve. Okay. So yes, so this was the basic thing about this tutorial. I don't want to go into more details anymore. I will stop sharing for the moment and I will let you try out various things. But I will be here for some more time in case you have questions. So, just remembered, maybe I can quickly tell you a bit about this sigma 8, which you had asked. So, let's see how to do that. I can just quickly do it. Maybe this will be the easiest. So, I will share my screen once more to just to show you what sigma 8 is all about. So I hope all of you can just give me a second once more. Yeah, I hope all of you can see this notebook. So suppose I have this cosmological density field. I construct a sphere of radius x. X can be anything. And then I construct spheres at different places, okay, in the cosmic density field. But every time I construct a sphere of radius x, and within that x, I calculate the density contrast. I call it delta x. Now, because the cosmic density field is not the same everywhere, this delta x will vary in each of these x. Naively, you also understand that if x is very large, then delta x won't vary. All of them will be 0 because you are averaging over the cosmic mean, basically. But in general, delta x will vary. And what you can calculate is the variance of this quantity, delta x square and its mod, because mean of delta x will be 0. But you can calculate, so delta x here, delta x there, delta x there, everywhere you do the square and calculate the average. This you can show will be nothing but an integral over k times the power spectrum times the window function, Fourier transform of the window function square. What is this quantity? This is the window function, and that will turn out to be wxk will turn out to be 3 sine kx minus kx cos kx by k cube xx cube. This is nothing but the three-dimensional Fourier transform of the of a hard sphere. Nothing else. Okay. So this quantity can be thought of as sigma square at scales x. Okay. Now suppose you do take x equal to 8 h inverse megaparsec. Then this quantity will be called sigma 8 square. Okay, this is a convention. Now sigma square x or sigma 8 both can be written. Okay, so now you can think of the power spectrum. Sorry, the power spectrum as AS times k to the power n s times the transfer function. Okay, this is the transfer function which tells you how the power spectrum would have evolved because different modes enter the Hubble radius at different times. Okay. So then what happens is you can calculate the sigma square x, and that will turn out to be AS, and you can put this this d cube k integral into a integral over just k. Do the angular integrals first. Then this will be k to the 3 plus n by 2 pi square t square k times this window function. Okay. Now you see this AS and sigma 8 are just related. So suppose you this t square k is known given the cosmological parameters. This is just this function known. So suppose somebody gives you AS, you can calculate sigma 8 from here. Suppose somebody gives you sigma 8, you can calculate AS from here, because this integral can always be done given all the other cosmological parameters. So that is why I said there are two ways of doing the normalization of the power spectrum. Either you do via AS or you do via sigma 8. Okay, but they are like closely connected. So this is what it is. Okay. Okay, so is there anything on the chat? If we make thinner, no. If we make it better resolution, isn't it? No. If you make the slice thinner, it will just contain less particles. So depending on, if you make it too thin, you won't be able to see the cosmic web. There are so few particles. If you make it too thick, then there will be so many particles. Again, you won't be able to make out. Okay, somebody says I have made the changes you said, but it is still showing the same error. So maybe there is a magic going on. I don't know. Okay, I'm sure you have removed some comma something somewhere. So just for completeness, I will share that tutorial screen once more, so that those changes, somebody can take a look at it once more. Okay, here we are. So it's K cube power spectrum by bracket 2 into pi square np dot pi square into 1 plus music data dot z whole square, comma. Then label this. Okay, so I don't know what is missing. Good. Okay, so maybe I can stop here, but I'm still here. If you have any questions, if you want to try running it for different cases, try to do that. People who have Linux machines or any machine, I mean, I can only talk about Linux machines because it's easier to install. People who have Linux machines, please try to install both the music and script if you are interested in these things. Try to install it on the Linux machine. Then you don't have to rely on Google Colab and things going away and so on. Okay, you can try to do it yourself, and then it is in your own machine. But you have to make changes to the notebook. As I said, the directory structures and things like that will be different, but you will be able to do that. Basic commands are all given here. So rest is just making it the way you want. Somebody said, can we run script code in laptop for higher box size? So it is basically RAM dependent, how much RAM you have. So firstly, higher box size is determined by music, not script. Script will run on whatever box you give it. So music typically requires something like 100 bytes per particle. So depending on how much RAM you have, you can calculate how many particles you will be able to do. Remember that whatever 128 cube to 256 cube, music will take numbers which are 2 to the power something. So you cannot run 150 cube in music. Okay, this is because of various other technical issues. We won't go there. So you can run 128 cube, 256 cube. The next one will be 512 cube. 256 cube you can run. I'm almost sure most laptops will have that much RAM. 512 cube is where at least my laptop doesn't run, stops running. So 512 cube will typically require 15 GBs, which most don't have. 256 will require 1/8 of that, like 2 GB. So 256 cube will run because most laptops now have 2 GBs RAM. I'm assuming most laptops come probably, your laptops may have 4 GB RAM or so on. So 256 cube will run very peacefully. 512 cube is somewhere you will be, it won't run. Your laptop may hang. Okay, so be careful. Okay. Was there anything else? Yeah, I guess if not, we can stop here for the tutorial. But if you have any questions, you can go post it on Slack or ask me on Monday. That's also fine.
Okay, so thank you very much, Tirt, for a very lively interaction session.